pleasure. So Lall is joining us from Auburn University. So we are still on the east coast of the US. And again, the title I have, I don't know if it's accurate, but it's about, actually, I can read from there. Yeah, so you can see it's about copper printing, which is one of the hottest topics in this industry. So the stage is yours, and yeah, good luck.
Thank you for that introduction, Kasha. Delighted to be here. Certainly privileged to present in the same session as a number of other NextFlex speakers. It was a pleasure listening to some of the earlier speakers talk on various aspects of flexible electronics. So this particular talk will talk about drop-on-demand technology, more specifically inkjet printed circuits and copper circuits that are additively printed with surface mount component assembly. So generally speaking, traditional circuits use plate and etch processes, as you are very well aware. The additive circuits that are being pursued using a number of print platforms, including the inkjet. One of the things that has to happen in order to realize functional FHE circuits is to be able to develop processes that are able to achieve parity, number one, able to demonstrate functionality, number two, and be able to perform the intended function in the presence of surface mount assembly. So it's with that intent that we embarked on this particular program. This is the results I'll be presenting today are from a NextFlex program that is currently ongoing. We are looking at a number of different print platforms, but today I'll primarily talk about a single material, which is the copper, and a single print platform, which is inkjet printing. The specific platform that we're using is Pixtro LP50 platform, and the intent of this study is to utilize inkjet printing to be able to look at the interaction between the print process parameters and the surface mount attachment of various types of components, look at their frequency response, quantify the statistical variance, and then more specifically look at a couple of different classes of applications, signal processing, as is mentioned here, and amplification type of applications. And the intent is to attach a number of components, look at performance with respect to theoretical expected performance, and see how the circuits actually perform. So with that said, those of you who are not familiar with inkjet technology, generally speaking, these operate using a piezoelectric transducer, where a piezoelectric transducer that's mounted up here in an ink chamber. Under the application of a voltage, it deforms and pushes out a droplet. And once the droplet is ejected, it basically is projected forward and deposits on the substrate to be able to form a part of a contiguous circuit. Generally speaking, there is a lot of process engineering that goes into developing a very good process, a drop-on-demand process. In this particular case, some of the print parameters that we have experimented with are listed here: on voltage, off voltage, on pulse width, off pulse width, phase width, which basically says that not all the droplets are ejected at the same time. Most of these heads have multiple nozzles. The one that we are using has 512 nozzles. The inks are fairly thin, so they are in the 20 to 40 centipoise range. Generally speaking, two of the inks that we are going to share data on in this study, the reference material is silver. This is something that people have studied quite a bit in the past. And the second material is copper, and that's what we largely focus on. So as you print a circuit, generally speaking, you're going to print a non-conductive line. That's because conductive particles are suspended in the carrier fluid. They have surfactants which have to be removed as a part of the curing process. And the curing process generally involves subjecting the parts to a high temperature for a certain amount of time. So silver, in this case, 130 degrees centigrade for 20 minutes. For copper likes to oxidize. So we have done photonic sintering. So this involves subjecting the parts to flashes of light. In other words, we are using high power, low energy type of a profile to be able to achieve that. So the way the process engineering typically happens is